Not to get too technical, but there's a few basic principles of resistors. If you had two resistors, R1 and R2, in series, the total resistance would be to add the two together. If one was 1500, one was 500, you'd end up with 2000 going through the system. Because they're just in series, it's like having one bigger one. But resistors in parallel, it's a lot different. The actual total resistance passing through this system would be R1 times R2 divided by R1 plus R2. Electrons would tend to go through the smaller resistor, or want to go through it. So it's a little more complicated, and this is the formula to do it. And the interesting thing that I brought this up for is resistors act like this, but capacitors, on the other hand, they actually are the two metal plates that are together. That's why the symbol is two metal plates that don't touch. It's frequency dependent, measured in farads, represented by C. And basically, they act oppositely. One stores charge, one resists the flow of electrons. And that's why they actually act a little differently. I'm just sort of demonstrating the fact that they're different properties in how they manipulate electrons. And a capacitor can store charge. And an inductor is basically a coil of wire. So as a resistor is represented as a squiggly line, an inductor is represented as, looks almost like a spring. And they use L, measured in henries. And these are also frequency-dependent components, just like capacitors. Resistance is not frequency-dependent. So that's how when you combine a resistor with an inductor and a capacitor, you can manipulate the frequency response of a circuit of a signal going through it. Transformers are basically two different coils of wire with some sort of center. And if a signal comes in here, the magnetic fields induce the signal to go through. And we use transformers all the time to isolate noise in audio, right? When they say, oh, it's a great piece of gear, it's got big transformers on the back. Basically what they're talking about is the signal coming in goes through a transformer system, so you leave any sort of problems that might have occurred coming into the piece of gear behind by not even connecting with a wire, just through a magnetic field. And you can isolate noise that way, you can balance cabling that way. We'll talk about what balanced and unbalanced cabling is when you hook up gear and why one's better than the next and so on. But transformers are used quite a bit. And transformers are very interesting because depending on how many coils on each side, you can actually get different power usages out. So if I have a voltage V and a current I going through here, you can come out with 2V and half I based upon how many coils are on each side and how much magnetic field induces electrons to move around. So, actually today in the studio I was using a transformer. I built a direct box. The direct box is where you plug your instrument in, like a guitar or a bass or a keyboard, and out the other side it comes out matched to go into a mic preamp so that you can amplify it and record it, right? And if you don't do that, it doesn't transfer the signal as well as it could into the microphone mic preamp. And most of what we're going to talk about is how to connect pieces of gear and how to get the best signal transfer so that you don't get any buzzing and so you get the most sound quality out of what you're connecting from one piece of gear to the next. Sometimes you have to go through transformers to do it. So transformers are very useful for all of that. Wire symbols, straight wire passes audio from one point to the next. We consider it in a diagram as being a perfect connection from one place to the next, but in reality it really isn't. Wires connected have a dot, wires not connected look like this. So when you look at your next schematic, as you fix your computer, you can see what's going on. Switches, components, I'm giving you a little example of how they look in a schematic situation.